Welcome to this lesson on one of the most fascinating phenomena in fluid mechanics, violations of the Scallop theorem. We're going to explore how reciprocal swimmers cannot move at low Reynolds number, yet droplets can self-propel through clever mechanisms. Before we dive into the Scallop theorem, we need to understand the Reynolds number. This dimensionless quantity determines whether a flow is dominated by inertia or viscosity. The Reynolds number equals density times velocity times length scale divided by viscosity. It represents the ratio of inertial forces to viscous forces. At high Reynolds numbers, inertia dominates. This is the regime where airplanes fly and humans swim. When you push water backward, momentum carries you forward. At low Reynolds numbers, viscosity dominates. This is the world of bacteria and microorganisms. The fluid is like thick molasses, incredibly viscous relative to inertial effects. For bacteria, the Reynolds number is typically between 10 to the negative 5 and 10 to the negative 3. This is an incredibly small number. Here's the critical insight. At low Reynolds numbers, there is essentially no inertia. If you stop moving, the fluid stops instantly. There's no coasting, no momentum. Now let's discuss the famous Scallop theorem, proposed by physicist Edward Purcell in 1977. Imagine a scallop trying to swim by opening and closing its shell. In our everyday world, this works because of inertia. The Scallop theorem states that a reciprocal motion, meaning a motion that looks the same forward and backward in time, cannot produce net displacement at low Reynolds number. A reciprocal motion is one where, if you play a video of it backward, it looks exactly the same as playing it forward, just in reverse order. If you expand in step 1 and contract in step 2, the fluid flow during expansion exactly cancels the flow during contraction. You end up exactly where you started. Why does this happen at low Reynolds numbers? Let me explain the physics. At low Reynolds numbers, fluid motion is governed by the Stokes equations, where inertia is negligible. The Stokes equation says pressure gradient equals viscosity times the Laplacian of velocity. Notice there's no time derivative. The flow is instantaneous and reversible. This equation is time reversible. If you reverse time, the fluid simply flows backward, along exactly the same paths. There's no memory, no history. Mathematically, if velocity at time t goes to negative velocity at negative t, the Stokes equations remain unchanged. This is the heart of why reciprocal motion fails. Now you might ask, if reciprocal motion doesn't work, how do bacteria manage to swim at low Reynolds numbers? The answer is they use non-reciprocal motion. Their swimming strokes are not time reversible. Bacteria use a rotating helical flagellum. The rotation is not reciprocal. If you play it backward, it looks different. This breaks the time reversibility and allows motion. Now we get to the really exciting part. Violations of the Scallop theorem. Under certain conditions, reciprocal motion can produce net displacement. The first violation we'll explore is droplet self-propulsion via the Marangoni effect using surfactants. A surfactant is a surface active agent, a molecule that reduces surface tension. Soap is a common example. Imagine a droplet in water with surfactant molecules on its surface. These molecules lower the surface tension. The Marangoni effect is a flow driven by gradients in surface tension. If one side of the droplet has more surfactant, surface tension is lower there. The surface velocity is proportional to the gradient of surface tension gamma. Fluid flows from low surface tension to high surface tension regions. When surfactant accumulates on one side, that side has lower surface tension. Marangoni flow drives fluid from that side to the opposite side. By Newton's third law, the droplet moves in the opposite direction. Now here's the key question. How does this violate the Scallop theorem? The droplet motion appears reciprocal. The answer is that the surfactant distribution itself breaks time reversibility. Surfactant molecules diffuse and advect in a way that is not reversible. The surfactant concentration C evolves according to an advection-diffusion equation. It has a time derivative which breaks the time reversal symmetry of Stokes' flow. Diffusion is fundamentally irreversible. It always increases entropy and mixes things. You cannot unmix a diffused substance by reversing time. So even though the droplet shape might change reciprocally, the surfactant distribution does not. This hidden degree of freedom breaks the Scallop theorem. Let's do a numerical estimate for the velocity of a self-propelling droplet. The droplet velocity u scales as delta gamma divided by viscosity mu times radius r. Delta gamma is the surface tension difference. For typical surfactants, the surface tension difference is about 10 millinewtons per meter. Water viscosity is about 10 to the negative 3 Pascal seconds. For a droplet of radius 100 micrometers, plugging in the numbers, 0.01 divided by 10 to the negative 3 times 10 to the negative 4 gives us about 100 micrometers per second. This velocity is actually comparable to bacterial swimming speeds, which is remarkable for a simple droplet with no active machinery. The second major violation of the Scallop theorem occurs in viscoelastic fluids. These fluids have both viscous and elastic properties. Viscoelastic fluids contain long polymer chains or other structures that can store elastic energy. Examples include mucus, saliva, and polymer solutions. The Deborah number compares the fluid relaxation time lambda to the observation time tau. It measures how elastic the fluid appears. Viscoelastic fluids have memory. The stress at any moment depends on the history of deformation, not just the instantaneous velocity. Imagine pushing a small object in a viscoelastic fluid, then pulling it back. During the push, polymer chains stretch. During the pull, they're in a different configuration. This asymmetry allows net displacement. The stress tensor tau depends on an integral over past strain rates. G is the relaxation modulus. This integral means the fluid remembers its history. This memory effect breaks time reversibility. When you reverse the motion, the history is different, so the forces are different. This allows reciprocal motion to produce net displacement. Experiments have shown that objects performing simple reciprocal motions can indeed swim in viscoelastic fluids, directly violating the Scallop theorem. The mathematical mechanism behind swimming in viscoelastic fluids involves normal stress differences. The first normal stress difference, N1, equals tau xx minus tau yy. In Newtonian fluids, this is 0, but in viscoelastic fluids, it's non-zero. For polymer solutions, the first normal stress difference is typically positive. These normal stresses create force distributions that are asymmetric in time, even for reciprocal motions. This asymmetry is what enables swimming. Let's compare the two violations of the Scallop theorem we've discussed. The Marangoni mechanism breaks time reversal symmetry through an evolving chemical concentration field that diffuses irreversibly. The viscoelastic mechanism breaks symmetry through the fluid's memory of past deformations encoded in polymer configurations. Both mechanisms involve additional degrees of freedom beyond just position. For Marangoni, it's surfactant distribution. For viscoelastic, it's polymer stretch. These violations have important real-world applications. Researchers are developing microrobots for drug delivery that use Marangoni propulsion. They can navigate through bodily fluids by releasing surfactants. Many biological systems involve swimming in viscoelastic fluids like mucus. Understanding these violations helps explain bacterial motility in complex biological environments. Lab-on-a-chip devices use Marangoni flows to manipulate droplets for chemical analysis and biological assays. Let me emphasize the critical difference between pure Stokes flow and these violation regimes. In pure Stokes flow, there's no time derivative, perfect time reversibility, and the Scallop theorem holds absolutely. With Marangoni effects, we add a time-dependent surfactant equation that introduces irreversibility through diffusion. With viscoelasticity, stress depends on history through a memory kernel, breaking instantaneous time reversibility. An advanced question is, what reciprocal stroke produces maximum displacement in viscoelastic fluids? The answer depends on the Deborah number and the frequency of the reciprocal stroke. There's typically an optimal frequency that maximizes swimming speed. The optimal angular frequency is typically on the order of 1 over the relaxation time lambda. This ensures maximum elastic energy storage and release asymmetry. Let me summarize the key takeaways from this lesson. The Scallop theorem states that reciprocal motion cannot produce net displacement at low Reynolds number in purely Newtonian fluids due to time reversal symmetry. Marangoni-driven droplets violate this by using surfactant gradients where diffusion introduces irreversibility. Viscoelastic fluids violate this through memory effects where stress depends on deformation history. Both violations require physics beyond the simple Stokes equations, either chemical transport or non-Newtonian rheology. These principles have applications ranging from understanding bacterial motility in mucus to designing microrobots for medical applications. The low Reynolds number world is counterintuitive yet elegant. The Scallop theorem seems to forbid locomotion, yet life finds ways around it through clever chemistry and material properties. This demonstrates how additional degrees of freedom can fundamentally change physical constraints.